Hi friends, in this video we are going to look at the binary search problem. This is a problem statement. Given a list of elements sorted in non-decreasing order and an element x, write a function to return index if the element x is present in the list, otherwise return -1. That is, if you are given an array of integers and also an element called x, you are supposed to return the index of x if x is present in the given array, or else we are supposed to return -1. Let's jump into the solution approach. Say for example, the element we are supposed to find is 9 and this is our given input array, that is -15, -6, 0, 7, 9, 23, 54, 82, 101, 112, 125, 131, 142 and 151. Here, as you can see, the array is already sorted in an ascending order. At first, I'm going to initialize two pointers, one named as low at the very first element of the array and the other called high at the very last element of the array. Now I'm going to compute the mid value based on the low and high value. That is, I'm going to add low and high and divide it by 2 to find my mid value. Since here our high value is 13 and low value is 0, 0 plus 13 will give us 13, which in turn divided by 2 will give us 6. Therefore, I have initialized my mid pointer to the 6th index of my array. And now we are going to compare the element to be found with the element pointed by the mid pointer in the array. As you can see, 9 is lesser than 54. It is clear that 9 lies somewhere between 0 and 6th index of our array. It's because beyond 6th index, as you can see, all the elements are going to be greater than 9. Therefore, we limit our search to the first half of the array. At first, I'll be moving the high index to the earlier mid position, and then I'm going to recompute the mid value, and then we'll obtain that 0 plus 6 divided by 2 will give us 3. Therefore, I move my mid to the third position. Again, we are going to compare our x value with the array of mid. As you can see, 9 is greater than 7, which indicates that 9 lies somewhere beyond the index 3 and within the index 6. We are going to eliminate the first half of the current array we have considered. So, at first I am moving my low to the previous middle position, and now I am going to recompute my middle. Since 3 plus 6 is 9, 9 divided by 2 will give us 4. Therefore, I move my mid to the index 4. Now, on comparing array of mid with the x value, since both are equal, which means that we have found 9 in the given array. Therefore, we'll proceed to return the index, that is 4. Now, let's look at the algorithm. Binary search can be performed using both recursion as well as iteration. At first, let's look at the recursive approach. Here, A is the given integer array of elements in ascending order, where I ranges between 1 to L. We are going to determine whether x is present. If so, we will be returning the index j such that x is equal to a of j, or else we will be returning -1. As you can see, this approach uses recursive function calls to determine whether the value x is present in the array or not. Let's look at the iterative approach. Here, given an array A of 1 to n of elements in ascending order where n is greater than equal to 0, determine whether x is present. If so, we are going to return j such that x is equal to a of j, or else we'll be returning -1. Clearly, here our iteration will be carried out until low is lesser than equal to high. Once our low value exceeds high value, then we'll break out of the loop and return. Now let's look at the time and space complexity. The time complexity is order of log n, where n is the size of the array. The best case time complexity for a successful search is order of 1, since only one element comparison is needed in case of a successful search. Whereas for an average and a worst case of a successful search, the time complexity is order of log n. It is the same in case of an unsuccessful search as well. While considering space complexity of the iterative approach, it is order of 1 since we use constant space. Now let's look at the detailed time complexity analysis. At first, we need to assume that the iteration in the binary search terminates after k iterations. At each iteration, the length of the array is halved. So let's say that the length of at any iteration is n. So at the very first iteration, the length of A, that is our array, would be n. And at the second iteration, as we have told earlier, it would be halved. Therefore, length of A is equal to n by 2. Again, in our third iteration, as you can see, n by 2 will be further reduced to n by 2 by 2, which can be simplified to n divided by 2 to the power of 2. Likewise, after k iteration, we'll have length of A as n divided by 2 to the power of k. After k divisions, the length of the array becomes 1. Therefore, we equate the above equation to 1. Now the equation reads as length of A is equal to n by 2 to the power of k, which is equal to 1. Again, we further simplify it as n is equal to 2 to the power of k. Applying log on the both sides of our previous equation, we tend to get log of n is equal to log of 2 to the power of k. Since log of a to the power b can be simplified as b log of a, we have reduced that to k log of 2. Further, log to the base a of a is 1. Therefore, here we can reduce log of base 2 of 2 to 1. Therefore, the time complexity is log of n.